Good afternoon everyone. Thank you for joining Mr. Ish for this video. We are nearing the end of the survey of differential calculus, and before we start getting into integral calculus, and I might be presenting some more topics on derivatives, but before we get into integral calculus, I want to talk about Newton's method. It's one of those topics which is very interesting because it relies a lot on the technique of functions with a little bit of the addition of easy derivatives. And the whole purpose of this technique or the method is the understanding of what an iterative process is. Iterative process. You all might have heard of this word iteration or iterative process. Basically, an iterative process is like an algorithm or a technique whereby you're depending very much so on the input from the previous step, where each step serves as the input for the next step. If supposedly you have a step 1, and the step 1 output will feed as the input of the step 2, and the step 2 output will feed as the input for step 3, so forth, and we'll just keep going until whenever the process is completed. Now the Newton's method is a very important method because you might not have realized, if you're looking on your calculator and you're looking at this specific function on your calculator, you know what I'm talking about. The square root. If you have ever wondered like how is a square root or any kind of a root calculated, any kind of a root, a square root where the index over here is a 2, or any root where you have an index other than a square, and have you ever wondered how these type of roots are calculated? You know, when you're talking about addition, it's actually easy. If you're adding something, you can actually mentally picture in your mind how you add. You just take something and you add something on top of that. There's a specific technique which is not hard, which relates with adding, subtracting, multiplying, dividing. Even taking in an exponent is not a difficult concept to comprehend. If you're doing like, let's say 3 cubed, you know how you do that. You just do 3 times 3 times 3. There's like a specific process which comes in mind. Like you're mentally easily able to grasp these type of operations, exponents, adding, subtracting, dividing, multiplying, all of that. But when it comes to roots, square roots or nth roots, have you ever wondered like how these processes are completed, or what's the algorithm behind this entire process? Well, that algorithm depends very much on this Newton's method, and I'm going to be talking about that. Exactly like how does one go about determining roots of any given number? We will be looking at that in this video. So this iterative process, which is exemplified by the Newton's method, is going to be a very interesting topic for today's video. Now just look at this basic function over here. Everything always falls back down to functions. Now just check this out. If supposedly someone said x squared minus 2 is equal to 0, if we were to rewrite it, we can look at something like this, x squared minus 2, and we can make it equal to 0. And when you solve for x, you take 2 on the other side naturally, and when you actually literally solve for x, you get plus and minus square root of 2, and you can run this through your calculator. You can get a good number on your calculator, and let's do that. If you do square root of 2, you get this number 1.414213562. But how did your calculator actually figure this out? What's the whole procedure behind this? Graphically, if you're looking at this right here, this graph over here, you know we're looking at a parabola, x squared, an open parabola which points upwards, minus 2 shifted down. Think back to this equation right here, a into x minus h whole square plus k. Lateral, horizontal shifting right or left, and up and down shifting, but we have x squared minus 2. You know, if you graph this out, your vertex is at 0 comma minus 2 pointing upwards. See, 0 comma minus 2, that's my vertex. Now this right over here and this right here, the two x-intercepts represent what the value is over here. You know, this one right here would be root 2 comma 0, and this right here would be minus root 2 comma 0. But we're trying to find out, based on the Newton's method and iterative process, how do you actually find the value of root 2? Graphically, this is what we're exactly talking about. So the Newton's method is going to depend on ability of 3 things. 1, you can somehow mentally graph your thing, your function. Number 2, you actually are able to come up with a function for what you're asking. You're able to, for whatever root you're trying to develop, you want to be able to convert it into a form of a function. And the other thing you need to be able to do is be able to at least come up with a derivative of that function. If you can do that, and by function and derivatives I'm talking about polynomials over here only. If you can do these 3 things over here, you can do the Newton's method. In the next part of this video right here, I'm going to show you graphically, in addition to this, I'm not talking about this anymore. in terms of what I'm showing you next. I'm going to show you exactly graphically what is the theory behind the Newton's method. Okay, check this out. Now the Newton's method in terms of graphically presenting it or explaining it is an iterative process. Let's just look again at this graph which I drew over here with the 0 comma minus 2, but forget the fact that it's at x squared minus 2 was equal to 0. Forget about all of that. The way you determine what this value over here is through an iterative process. Same thing here and same thing here. You basically come up with some arbitrary value. Whatever that arbitrary value is, we'll just call it x1, and you project what it might be over here. And you know that projection over here, you can easily figure out it would be x1 comma y, right? But you're going to have to come back to the whole concept of tangent lines. If you draw a tangent line at this point over here, right, it looks something like this. Remember, I'm not drawing anything to scale. Now from this intersection of this tangent line to this x-axis, you draw another point. This represents another value over here. From over here, you draw another tangent line, right? And the intersection over here, you draw another one. If you were to zoom in, because this thing is so zoomed out, you don't see it clearly. If you were to zoom in or like get more focus onto this, you would see something like this. Now I'm going to try to draw it clean, but let's see how it works out. We have an intersection over here of our curve. We have to be a little bit more big over here, and you'd see one value coming over here, a tangent line over here, another value over here, another tangent line over here, another value over here. So you'd see 3 values over here. The more values you can draw, the more accurate will be your result. But this is what I'm talking about. With each new point, you get a new tangent line, and that tangent line intersects the x-axis. You make another point, and you draw a new tangent line. It intersects at the x-axis. From there, you make another point until you're getting so close each time towards your root. You can take this to a very large, lengthy process where you can keep doing assumptions upon assumptions upon assumptions. As you do more and more of those assumptions, you get closer and closer to your root. I want to show you by an example. And look over here, I only have drawn over here 3 different assumptions. Each of these tangent lines represents an assumption. Here's 1, here's 2, here's 3, and my root is still away. But the closer you get to your root, the smaller the distance, right? And it becomes, these lines become more cramped, but they get cramped more to us in terms of the human eye watching it because our resolution is not good. But on the computer, you can squeeze in many of these tangents and many new points. The point I'm trying to make over here, I can graphically only show you 3 before it becomes a mess. But if you can go up to assumption number 8, you can get a very accurate answer, so close that you will actually have the true root available. But in this Newton's method, you don't have to go up to assumption number 8. But if you did, you could get a very easy answer to your root. But you can stop at like assumption number 3, 4, or 5. Now you might be wondering, what's the point in doing all of this if all you can do is just pick up your calculator and look at the square root, or you can look at this 1 over y root, and you can just determine your nth root no matter what it is, like cube root, 4th root, 5th root. Then what's the point in learning all of this process? Well, the point in learning in this process is because it ties in many concepts. It ties in the concepts of rates of change, functions, derivatives, and assumptions, and it is an important algorithm to be aware of. If someone were to tell you to find this right here, like 17 to the cube root, and you couldn't use a calculator in any way other than just using the basic multiplying, dividing, adding, and that, but you couldn't actually use any kind of a root in your calculation with the calculator, how would you go about doing it? Well, I'm going to show you in this video how we would go about doing it. So what's the actual process for the Newton's method? Well, we're going to break it down for you over here. The process will be this. Number 1, you're going to first find a function. You'll convert your problem or what you're trying to find into a function. That's step number 1. Step number 2, you're going to determine its derivative. Remember, we're talking about polynomials over here. It's going to be very easy. You know how to do polynomial derivatives. You use a power rule. It is that easy. Ax to the power of b, you know the derivative of this is bax to the power of b minus 1. Easy. You've seen this and you're good with that. You don't have to do any graphing if you don't want to do. Graphing is purely optional and it's not a requirement by any means. Step number 3, you're going to make an assumption for your very first value. Assume what the value x1 is, like your very first assumption, and come up with some specific number over here, and that number is going to tie in through the iterative process that you'll see. So the step number 4 will be an iterative process, you're going to run your entire process through a series of steps where each of the previous step value will serve as the input for the next value steps. Now supposedly you're on step number xn, step number n, you're going to take the value you had from the previous step, that's why I'm saying n minus 1, the previous step, and you're going to minus it from what you're going to do over here. You're going to put this value into your function, the previous step value into your function, and you're going to put the previous step value into the derivative of your function. And when you see all of this play out, you'll see exactly what I mean. You can go through step number 1, step number 2, 3, 4, 5, as many steps as you want until you get to your nth step or your n step, and you can stop over there. And then you'll actually see your final answer as a result of all of this. But the most important step over here is basically this one right over here, where you're doing the series of steps. When you see this out, you'll see exactly what I mean. The previous input will be served in the next series of steps. The previous step, you'll take that value and you'll put that same value into the function value and into the derivative value, and you'll carry it out through this calculation process. When I show it to you in process, in procedure, you'll see it exactly. It's not hard at all, but it's interesting. So let's look at a specific example, an easy example, then we'll take it up a little notch, and then we'll see something more interesting. So we want to use a Newton's method now to see what the square root of 2 equals to. And when I'm showing you this video, I cannot use the square root button on the calculator by any means. We cannot do it. So the first step, I told you, you have to convert this into a function such that your function would give you the value root 2, that you could graph it. So with this framework over here, right, we basically have to come up with a function over here that will help us give us an answer for this, what root 2 is. And you can write it as this x squared minus 2. If you were to take this equation over here and make it equal to 0, x squared minus 2 is equal to 0, and you solve for x, you'll get x is equal to plus and minus root 2. So you know you're on the right track over here. We've gotten our function over here. Remember, we need in the formula, we need the function and we need its derivative. You know what the derivative of this function is. You just follow the power rule. X squared derivative is a 2x. Derivative of a constant is always 0. So we have everything we need over here, right here, the function, the derivative, and we need now nothing more than the very first assumed value. What is my first assumed value going to be? What do I think when I'm thinking root 2? I know it cannot be a 3 because the square root of 2 must be a small number. How about as my very first value, I just take x1 equal to 1. That's going to be my assumed value. Now look, we have to do the series of iterative processes. Remember I said if you go up to the 8th step, you'll get the most accurate answer. But we cannot really do 8 steps over here because of the space limitations we have. We have to be a little reasonable over here. So let's look at a step number 2. And you know the formula I presented, each step depends on the input from the previous step. You're going to take the x1 value, which is right here, and you're going to minus it. And if you remember correctly, the formula, I'll put it over here, for any step, let's just not even do it with the subscripts. It would be f of x divided by derivative of x. X minus f of x divided by that. Whatever step we are on, we're using the previous step values. Now look over here. The previous step value, x1, is a 1. And we're going to minus it from by putting this value right into this equation. What's 1 squared minus 2? See, you're going to put it into f of x. You're putting this value into f of x. What's 1 squared minus 2? It's a minus 1. And you're going to put the same thing into your derivative. What's 1 into that derivative? It's a 2. Now solve this out. What do you get? You have to bring your calculator. Well, maybe not, because 1 plus 1 over 2, you're getting a 3 over 2. You want to stay away from fractions, so we're getting a 1.5. That's our answer here for this step. Now look, we go to the step number 3, where we're looking at the third. See, this is my iterative step 1, iterative step 2, and iterative step 3. Now each step will take the input from the previous step. This 1.5 will come right over here. Now we'll put 1.5 into this function right over here, and we'll carry it out. Let's use our calculator. What's 1.5 square minus 2? See, 1.5 square minus 2. 1.5 square minus 2, I get a 0.25. 0.25. And remember, the more decimal places you take, the better it is. Now 1.5 into the derivative times 2 is a 3. You have to carry this out. 1.5 minus the quotient of these two numbers. 0.25 divided by 3, I'm getting this 0.08333 repeating. I'm going to add that to 1.5, and I'm getting, look at this number, 1.416666. I have to write all of these numbers down to stay accurate. If I don't write all of these numbers down, I lose on accuracy. Now let's look at step number 4. Now this entire number over here comes right over here. Remember, an iterative process. I'm going to take this entire computation to step number 5 minus. Now look over here. I have to take this entire number and run it through this formula into the f of x and in the derivative. I take this number and I run it over here. How about I save this number? Square it minus 2. I get this number here on the top. I get 6.94444. I'm getting 1, 2, 3, 4, 5, 6 fours. 2 times 10 to the minus 3. And you take this same number and you multiply it by 2, and what do you get? Because you're doing the derivative part now over here. Multiply it by 2 and I get 2.83333333. It can be messy, but it's good. Now we do this divide and we take this entire computation. Let's see what happens. I'm getting here this number right over here. We'll check this out. I'm getting 1.41421567. Remember, I'm saying I'm not using the radical button by any means. I'm not using the square root button. Now for the 5th step, the 5th iterative process, this number has to come over here, and now this number has to run through the same loop that we're talking about. 1.41421568 minus. We're gonna take this number, has to run through this function now. When I run it through this function here, to this top part, I'm getting over here is 6.00828 times 10 to the minus 6. Now I'm going to take the same number and run it through the derivative. I'm getting a 2.2828431373. Now we're going to do this entire computation, present an answer, and we'll stop over here. I'm getting this 1.4142. I'm going to write the entire number down, what I'm getting. I'm getting a 1.4142135556, and we stop over here. Now what we do is we bring our calculator and do square root of 2 and see what we get. Square root of 2, I'm getting this. And I'm going to write this. The square root of 2, what I'm getting on the calculator is 1.4142135562. Let's compare this number to our number right over here. Let's see where we start differing. We have 1.4142, 1.4142, and our numbers are different only here in the last two right here. Other than that, we're all the same, and I haven't used the calculator for anything but the basic computations over here. I've not used a square root or the radical button in any ways. But had I carried this to the 6th, 7th, and 8th iteration, we would have gotten the exact answer, and we would have been good. The Newton's method would have been fulfilled with that. But you can see over here how the process is. You start with an assumption. That assumption will serve as an input for your next step. The next step will follow this scheme right over here, where the previous input minus the previous input into the function divided by the previous input into the derivative, and that new answer serves as the input for the next series of steps, and you see how it plays out. So this was just the square root of 2. You can take literally any number and you can carry it out to the same process, and you can get a good radical answer or root answer. If you look at this graphically over here, x squared minus 2 right over here, this root over here, well, this is the root we've calculated. You've also calculated at the same time the negative root. All you have to do is put the plus and the minus right here, the plus and the minus, and these are your plus and minus roots, and you're done. Now look at the question which I'm going to challenge in this next part over here. Remember at the slightly near the beginning, I put this over here, cube root of 17. I believe it was cube root of 17 I was doing, showing how we could actually go about doing this. I didn't actually calculate it, but I hinted towards this. Let's actually calculate this. You know, the first step is to come up with a function. Your function will be this. It will be x cubed minus 17. If you look at it, if you do x cubed minus 17 equals 0 and you solve for x, you get x cubed is equal to 17, and then x is equal to cube root of 17, and this is exactly what I'm talking about. So this right here is your function right over here. That's step number 1. Step number 2 is to determine its derivative. What's a derivative? Use the power rule. It'll be 3x squared, and we're done. What's step number 3? Come up with your very first assumption. We know 4 squared is a 16, but we're talking about cubes. We know 2 cube is an 8 and 3 cube is a 27. So our assumption should be somewhere between 2 or 3. It doesn't matter if you start from a low number, you'll work your way upward. If you start from a higher number and where your assumption is higher than what it should be, it'll work its way down along the x-axis towards the proper number. So I'm not going to pick 3. I'll actually pick over here as my assumption 2, because I know 2 cube is really an 8. So I'm really far away from 17, but I'm just taking this as my assumption. I could have taken 2.5. You can do that. I'm just picking this. And you know our framework is this. It's always the number from the previous step minus that same number put into your function divided by that same number put into the derivative, and you're always running it through this scheme. So we have our x1. Let's figure out what x2 would be. x2 would be the previous number minus this number placed into this function divided by this number placed into its derivative. So let's do that part. This is where the calculator is coming into place, but only for the multiplying and dividing operations. We're not using the calculator for any kind of roots. Remember, I cannot use this button here on my calculator which looks like this, nor can I use this type of button, x to the power 1 or y, which is the same thing as you doing a cube root, or none of these type of n root buttons. We cannot use these on our calculator because we're trying to determine how does a calculator do all of this. Like, what's the algorithm involved? It's this type of algorithm, an iterative process, the Newton's method. Anyhow, let's put 2 over here. 2 cube is an 8. 8 minus 17. 8 minus 17 is a minus 9. Let's put 2 into the derivative. 3 times 2 squared is a 3 times 4, which is a 12. Let's come up with a decimal answer. Always use decimal answers because fractions are not good enough. So we bring our calculator and we solve this part. And let's do it. 9 divided by 12 plus 2, I get a 2.75. So it's telling me that I'm working my way upward because my original assumption was too low. Now, well, let's look at step number 3. Remember I said you have to go up to step 8 to come up with a very accurate answer, but we'll stop at step 5s or 4s based on space limitation. So this 2.75 serves as the input of the third step, minus, now you have to run 2.75 into this f of x part and 2.75 into this derivative part. And don't confuse this by divide line over here. We actually have the divide line over here. This was just me identifying what was what. 2.75 into that. 2.75 cube minus 17. I'm getting, remember you have to write all the numbers down here. 3.796875. And 2.75 times 3 and square of it. 2.75 square times 3, I'm getting this. 22.6875. When we solve this out, what do we get? And over here I'm getting this number. I'm going to write them all down, all the place values. 2.5826444628. Now this input over here will become, this output will become the input for this step number 4. And let's do 2.5826444628. And we have to now run it through this procedure over here. The same value. We'll do x cubed minus 17. Here on the top in the numerator I get a 0.226377259. Here in the denominator, when I run it through the derivative, the same value through the derivative 3x squared, I get 20.0105983. Now I have to actually do all of this right over here. I'll present an answer. And you know we had a minus sign over here. So I'm getting over here a 2.5713311512. The output of the fourth will serve as the input of the fifth. And we will stop at the fifth iterative step. Now, this value over here will serve through this function and the derivative process to give you the quotient outcome over here. Let's see what we get. 2.5713311512. Let's run it through the numerator part, exponent 3 minus 17. Over here I'm getting this number right here in the numerator, 9.901824 times 10 to the minus 4. In the denominator, what will we get? Let's see. We'll take this number and run it through the derivative. Here I'm getting this right here, 19.83523723. See, here we're actually finding a cube, so we're not doing a square root, we're finding a cube root. But that's good. Now let's do this entire computation and put an answer over there. When I do this entire computation, I get this number over here. Due to space, I'm going to put it right over here. 2.5712815992. This is the number I'm getting using the iterative process, the Newton's method. I'm going to put the number over here when I actually use the calculator for the cube root of 17. We'll do the cube root of 17 and see what we get. We just write 17 and we can find the cube root button over here and cube it, and I get this number, and I'm going to write it all out over here. Then we'll compare our calculator with this result. 2.5712815991. Now let's compare it to this result over here. These two results have to be compared. We're accurate 0.57128.159. The only difference we have here is in the last numeral. Everything else checks out as being the same. But look over here. With this result, we are accurate up to 1, 2, 3, 4, 5, 6, 7, 8 decimal places. Had I taken this up to the 6th or the 7th, we would have completed that and we would have been accurate. The more iterative steps you take, the more accurate you are towards the true root. Anyhow, we found the cube root of 17. If you could graphically even do this, you could just graphically look at this. It would be x cubed minus 17. How do you graph x cubed minus 17? It's a cube root function shifted down by 17 units. Let's do a rough graph right over here. It's nothing more than translation, vertically translated. A cube root graph shifted down to a vertex of 0, minus 17. You know what a cubic function looks like? It always goes to the origin like this. But this graph will be going through this new vertex of 0, minus 17. This right here is the root we have just determined. This right here, intersection of this curve with the x-axis would be 2.57128.159, and that would be the representation of this root. There would only be one root over here because it's a cube. You're not going to have a root on the other side, a negative root. It'll only be a single positive root. Anyhow, this right here was a Newton's method for the cube root. We'll go back now. I'm not going to present any more lengthy examples. I'm just going to go back and revise some of the procedures in the remainder of this video. So now in the remainder of this video, having completed 2 examples to completion, let's just look again and revise the theory behind all of this with some practical significance to it. If supposedly someone was telling you to find the 7th root of this number 15, your first step here should be the determination of the function such that if you were to solve for x, you would get this, and you would be looking at something like this, x to the power 7. Your root over here, your index, is always the exponent on your x, alright? That's what we're looking at over here. And you want to put like a minus over here and equal it to 0. The reason why you want to put a minus over here, that way you're not taking a positive and making it a minus and doing a root of a minus number. You can do odd roots of a minus number, but you want to always frame it in this way. Because when you solve for this, you get x to the 7 equals 15, and you get x is equal to 7th root of 15, and this will mirror exactly what you're trying to find. And you know the next step, this right here is your f of x step. The next step is to determine the derivative, which you know is easy. You always look at this function part for the derivative. Remember, the function is going to give you that derivative using the power rule. Always look at your function. This right here is your function, the function form. Get the derivative of this. What's the derivative of this? It will be 7x to the 6th. Alright, and then you know what the framework is. You always have to start with one assumption, which is your assumption number 1, what value it is. Try to come up with a good value. Think about it. What number multiplied by itself 7 times will give you 15? If you did 2 to the power of 7, that's like a pretty large number. I believe that's 128. Is 128. So you know you cannot pick 2, but you cannot pick 1 because 1 exponent 7 is just a 1. You could pick 1 if you wanted, but you'd be pretty far out, and you can pick some number like 1.5. Your first assumption here could very well be 1.5. It could actually be 1 or 2, except 2 will be so far out, it'll come back downwards. 1 will be so far away and it'll go forward and become larger through the assumptions. Then the next part is just the iterative steps. You're just taking it such that the input of each new step is the output of the previous step. So you're basically running it through that scheme. Okay, so the next step would actually be the assumption of the next step would be your previous step, and you're going to run that previous step value through this scheme. As you see, the second step would rely on the first step value originally, and you minus from that the first step placed into the function divided by the first step number placed into its derivative. And you'll keep doing this at least for several cycles. Anywhere between 5 to 8 is a good number of cycles to get an accurate answer. And that's basically the procedure you're going to use for the Newton's method. And the procedure is not hard. Start with your original function, determine its derivative, come up with some sort of reasonable approximation, then run through the iterative steps. I want to show you graphically again in the next and the last part of this video the whole theory behind this with regards to the tangent lines. When you look over here at this graph, it's just a partial graph. You have the positive x-axis and the positive y-axis. Here's our origin. You have a certain root coming over here, or true value over here. If you actually were to look at whatever this function was, I don't know if this is an even root or an odd root, it doesn't really matter, but you would be looking for this value. You want to get the exact value. You would start with a specific assumption you'd make. Let's say this is x1. You don't even have to pick a value out. You could have picked your assumption value over here at x1 right over here, and then you'll move this direction. If you start way out over here and your root is over here, you're going to end up moving this direction with your remainder of assumptions, because the first step, when you run it through that formula, of this formula where I'm just writing a rough schematic of it, it will automatically adjust you for this direction going downwards or for this direction going forward. Anyhow, assuming this was your first assumption of x1, what you will do, you're not actually doing this, but this is what's actually happening behind the lines graphically. Your value ends up coming over here, and the coordinate over here, as you know, is x1 comma f of x1. That right there. A tangent line this is what the algorithm is doing. A tangent line is being formed and it intersects over here. Remember, I'm not drawing things here linearly straight or very accurate. I'm just giving you a rough idea. This intersection over here of the tangent line with the x-axis represents what will be the input. It was the output of your first step, which served as the input for your next step. And you draw this up over here. You're not literally drawing, but this is what the algorithm is doing. This over here is represented by x2 comma f of x2, your x and y values right over here. Another tangent line is somehow drawn magically, and it ends up intersecting over here. You draw, hypothetically you draw, and this represents your third assumption. And a third tangent line is drawn over here, and it ends up right over here, and you draw a fourth one, and that represents right here your fourth assumption. As you get closer and closer, you can not visually squeeze in any more lines, but theoretically you can keep squeezing in more and more lines, because those tangent lines become their slope changes of the tangent line, such that you can keep drawing more and more tangent lines, or the computer can keep doing it until where the computer decides that yes, we are close enough to make an approximation, or we are close enough to the actual root, and your final approximation is such that it is actually on the root. It is actually on the root. And that right here represents, through the series of iterative steps, what your actual root is for what you're trying to determine. But again, this right here is the theory behind this Newton's method. It is a series of iterative approximations which depends on you coming up with a function, coming up with its derivative, and you coming up with an original assumption. That original assumption, either too far out or too far behind, will automatically adjust during the remainder of the steps. You'll keep carrying out the specific steps until whichever step you want to go to. As I said, step number 5 up to 8 is sufficient. I've shown you with 2 examples. When I went up to step 5, I was only differing by the last 2 or the last digit. Everything else was 100% accurate. So again, this right here is the Newton's method, elaborated to the best of my abilities. I know it's not an easy subject, but it's not a hard by any means. You just have to have basic understanding of functions and polynomial derivatives, and the basic understanding of what an iterative process is. I hope you enjoyed this video. Please stay tuned as we have many new topics on the way. Thank you for watching. Have a nice day.